All right. The blue curve represents basically a unique massive star supernova. We're doing luminosity over time, and these are in units of the luminosity of the sun. And so you can see that a a supernova is about 1 billion times brighter than the sun, maybe 10 billion times brighter. A white dwarf supernova is this red curve, and it is unique and different. And every white dwarf supernova looks like this because they all occur from the same physical mechanism. Right? Supernova are so much more massively luminous than nova, and the nova are due to hydrogen fusing to helium on the surface of a white dwarf. A supernova is going to be either a massive star supernova and it leaves a remnant of some other, a black hole or a neutron star, or it's going to be an explosion of the white dwarf, which means there's nothing left. The matter is going to be spread out into space essentially as gas, as the carbon fusing into other elements. Right? So the light curves differ, the spectra differ because the white dwarfs don't have that much hydrogen compared to a massive star. And so you won't see the absorption lines from the material in the spectra from the white dwarf. So I mentioned neutron stars. All right, when we have a massive star supernova, there's some remnant left over. The core still exists. And we talked about the ball of neutrons that's left in the core. Protons and electrons form this ball of neutrons, and it's irreversible. The neutrinos that are formed leave, and so there's nothing to make them back. And so you have this ball of neutrons that the outer layers of the star bounce off of. And so you're left with a remnant of gases and a core in the middle. And that core is a ball of neutrons. The neutrons are held up by their own degeneracy pressure, which is significantly stronger than electrons. And so this is a very dense ball of matter. All right, we talked about the formation of protons and neutrons. Protons forming into neutrons by absorbing up electrons and giving off neutrinos. Right? So a neutron star, this is a small city. This is the capital of Michigan. And this is effectively the size of a neutron star. It's not that big, about 20 miles in diameter. Right? So they're very small objects, and there's no fusion going on. They just have some thermal energy. We ask, how do we know that they're there? All right, and a hint is that we see some weird stuff. We see stars that vary in intensity over seconds, and that's unusual. All right, so the very first discovery um, occurred using radio telescopes, and this was in the late '60s. Um, an astronomer, a grad student, Jocelyn Bell, found an object that instead of varying over months like most variable stars, it varied in radio emissions over seconds. And these pulses, they didn't know what they were coming from at first. They called them pulsars. And we now know that this has to be a neutron star that's spinning and putting out energy towards us. Right? So if we look at the Crab Nebula, we can find a remnant in there which pulses, in this case, 30 times a second. So a pulsar is a neutron star that beams off radiation along a magnetic field axis, which doesn't happen to be correlated with its rotation axis. So it sweeps out like a lighthouse. Right? The lighthouse passes a beam of light outwards, and the pulsar passes a beam of light, and we see the ones that point at us. Right? Other neutron stars may do this, some may not, but the only way we see the pulsar is if the beam's pointed at us.